ain't another car inside. I passed the graveyard, the headlights flash. It looks like I'm racing tonight.
Let's go ahead and call our meeting to order. This is Open Research Institute's meeting for the 20th of January. And what we do at this meeting is we talk about what we have done and what we have planned to do. If we need any resources, if we have any roadblocks. So that's kind of the format of our roundtable. And we have a agenda today where we'd like to talk about any OpenCPI progress from Aaron, and then Opulent Voice progress from a number of us here. And then there's some FOSDEM preparations. It's a conference that's coming right up on the 31st January and the 1st February. And Everest F5OEO has very generously agreed to present Opulent Voice and Open Research Institute work at FOSDEM. It's very exciting. And then we have an update about the AMSAT-UK Mode Dynamic Transponder project. This is something that is targeted for the FunCube Plus satellite launch in the relatively near future. So this is a sort of a FPGA and general purpose processor communications project. So we're helping out to try to figure out how it can be done and to do some prototyping for that. And then how we can leverage this particular project, this mode dynamic transponder work, that we can get it to work for high Fourier, because it directly applies to the receiver for the uplink receiver. So we know that we want to do a polyphase channelizer, multi-rate channelizer. We already have taken a good stab at this with Theseus Cores, which is an open source multi-rate project. And that has informed us. We've demonstrated it a couple of times, been a couple of years now, and we know that that's the most efficient way to do it. But doing this prototype for AMSAT UK actually will help us quite a bit in moving things very much forward, so that we need something to receive all of these wonderful Opulent Voice channels. And this is where that stuff starts actually working, being prototyped and being simulated. And then, of course, to us, the most important thing is getting it to work over the air. So that's kind of our agenda. That's not a limiting agenda. That's just what we are trying to talk about today. So if anybody has anything else that they want to talk about or share, that's absolutely welcome. Just wanted to make that very clear. So let's go ahead and start with the OpenCPI. And Aaron, if you got anything, you have the floor.
Sure. Yeah. So this last week, I was testing the encoder on hardware with the GSE pattern on the processor sending data over. I was only able to get one message through, so I started debugging. I added ILA to it. I noticed that in my application, I was configuring the registers that I was enabling the dummy generator, which then that blocks the AXI data from flowing through. So I did switch that over, but I was still not getting data to flow through. Within the ILA, I was able to debug and notice that the way that I'm configuring the encoder is upon initialization, I'm writing all the registers to 0. So I think there's something that I'm writing to 0 that shouldn't be written to 0. So this week I plan on fixing the initialization such that it doesn't write every register to 0, and rerunning the test to see if I get any further more than just one GSE padding frame to be sent through the encoder. So that's my update for the week.
Wow. Okay, that's a lot, and it actually is a familiar problem. Because in a lot of the communications designs that we encounter, that we deal with, we do have things like dummy frames. We have the same sort of setup in Opulent Voice, and we put in dummy frames in order to kind of extend out the end of the transmission, just in case queuing takes a little bit longer or somebody comes back and wants to transmit more. And the choice about where that dummy frame is sourced from, it's usually programmatic, like it's been generated from code. It's not being generated from external data source. So the control of switching back and forth is pretty critical. And yes, that's a familiar problem, that it wipes out configuration.
Yeah.
Is a blocker. And if you're using AXI, which we are too, then yeah, it gets kind of interesting very quickly. So I think you've you've come across a
A
very
familiar pattern.
interesting. Yes, it is.
Yeah.
It's a familiar pattern, and it's one of those things that if you hit it, you're like, ah, yeah, I'm on the right track. So, yeah,
Yeah.
right on. No, thank you. This sounds fantastic, and looking forward to hearing how it progresses from here.
Yep.
All right, and Paul, you want to talk about any Opulent Voice um, progress? Both you and then Matthew, you can take over right away.
Okay. Um, as you recall from last week, we had achieved the ability to transmit from one Libre SDR and receive on another Libre SDR. And I demonstrated that live here, whether you liked it or not. And after that, um, Everest decided that it was a good time to integrate Opulent Voice with his Tezuka project and wanted to test in the with one of the Libre SDRs in the remote lab. So I took one of the SDRs, in fact, the old one that we've been using for a while, and I moved it into the actual remote lab, hooked it up on the remote lab network, and gave him access to it. We did some tests, he and I, with some cooperation. And what we found was that it couldn't transmit, and therefore the loopback was not working. Um, that is still an open issue. We don't know why. I assume Everest is looking into that. Um, in order to find out whether it could receive, Everest asked me to move another Libre SDR into the test setup and transmit with that known able to transmit Libre SDR into the receive port of the one he has control over and see if it could receive. And we tried that, and it sort of did, and sort of didn't. Um, there are many confusing aspects here. We were able to reproduce um, the observation that we had here of losing the first frame of every transmission. Um, but other things were also going on. And I eventually decided to move the third Libre SDR in there too and have it uh, sort of be the tiebreaker and try to receive the transmission while the Tezuka version was receiving the transmission. And it's still able to receive. Um, so there's something that's not quite right with receive as well. Um, that has not been investigated enough to know the answer yet. So that's where we're sitting. Meanwhile, over the last day or two, I was trying to set up ability to work with all three of those from my workstation here in my lab. And I found out that it's not a good idea to run two interlocutors on the same Mac. Um, Even if they're hooked up to separate audio devices, they somehow interfere with each other. And I guess that's not too surprising because the Mac doesn't really have native support for lots of different audio channels running together. There are third-party programs that can do that, and I have some of those installed. And for all I know, they're contributing to the interference at this point. I haven't tried running without them. That just occurred to me. Um, so there's progress and blockers, and we don't know what they are. Um, there's a couple of different outstanding bugs that are problems with getting everything to really work right, and uh, most of those are in the HDL where I can't see them, and there's stuff going on uh, with Interlocutor and Dialogus as well. So we're not done.
Sounds like we have plenty to do. You might be burying the lead a little bit because this sort of kind of indicates that we can successfully transmit over the air, and therefore we can say that we've had a lab call.
We have we did that during the meeting last week, so that was last week's lead. um, that's we over the air meaning over a coax cable. So far, we haven't been hooking up antennas, but I don't expect that'll make any difference. We'll try that eventually. It'd be nice to have, some filters and power amps to be able to do it over a real path and not just side by side on the bench.
Right. Yeah, I think that that will be really fun. So we have a couple of sites that we can try this out at just amongst ourselves. And then we have several sites on mountaintops here in Southern California that are very interested in putting one up but in order to do that, we do have to have, better power supply, better amplifiers, better filters, and some sort of, more durable enclosure, at least for finger poking to make sure that, it doesn't get physically altered in an unreasonable manner. So we're close to that sort of thing. So it will start out with some small local separation, and it'll be truly over the air, like over the antennas and stuff. But we will need the very basics of sort of the power amplifiers, probably very similar to the one that Oscar used for the sounding rocket test. And then also some filters because they did not have to worry too much about filtering because of the experimental license. But the bands that we're looking at will have some more regulatory requirements that we need to comply with, and that's a good step. So all this is good news, not bad. But that's in the very near future. So I think you're saying that last week was a good time to declare a lab call, because I think that's a big milestone. So I think we're there.
It's a one-way lab call, so it's half a lab call. We haven't tried doing full duplex. The full duplex is not a thing for the high Fourier target. For terrestrial targets, it may be. So we'd have to at least do split frequency to do that in the real world. But doing it in the lab, we can probably get away with a lot.
Okay.
Oh,
Well,
another thing I want to mention, which I remembered and then I immediately forgot, of course. It'll come back to me. I'll come back to you later.
Sure, no problem. No, thank you. This is a tremendous amount of work, and we've covered a lot of ground. I think that the January newsletter will have plenty in it about all of this and more. And just thank you very much for everything you've done. It's been fantastic. Oh, go ahead, Oscar.
Yes, hi to everyone, and glad to be here. I actually had my alarm set up to be here earlier, and it didn't go off. So suddenly I say, "Oh, it's late." Anyway, I want to do something. I want to keep busy. Send me the list of the equipment required for doing this experiment. The Pluto or the new device that I was checking last week, and the frequency that you want to work, so we can work with the antennas amplifier and work that, because that takes a little time. It doesn't come out easily until it's purified correctly. So I have a couple amplifier here, but that's for the 70 centimeter band.
Yeah.
The preamp is a broadband, and then I have to work with the filters, as you said. So at the same time, I can work on that. So I will be honestly, I would love to work on that.
Okay, thank you. Yeah, we'll start talking. I'll bring you completely up to date with the bill of materials and as far as we know, because we're plowing into this and a lot of new equipment for us too as we kind of sort of transition from having the Pluto being Pluto SDR kind of focused, and when we outgrew that FPGA working up to essentially Pluto clones. And this is a whole giant collection of things. And yeah, the supply chain is a little weird, but at least the amplifiers and the filters, I think those are more understandable, more predictable. These are things that we can sort of develop as a bill of materials, and we can say, okay, here are the requirements for sure. And yeah, but I think we know some of those, but we need to firm that up and get that. Yeah, we need to actually start including that as part of the design rather than just in the lab, just a simulation, and just kind of a very experimental, sort of uncontrolled thing. The fact that we're using minimum shift keying is great. This reduces a lot of the filtering requirements just because of the nature of the modulation. It's really quite amazing. But you still need a transmit filter. You still do. But the requirements on that filter are less than if you are using other modulations. And the requirements on the amplifier are less because it's constant envelope. So we get a lot of benefits from the design choices, but now's the time where we need to actually kind of firm it up and pull it together and say, okay, use this, not that, or you have to be at least this tall to ride, you know. So thanks,
And
Oscar. I'll definitely
and to be sincere, it's not just to buy one. You have to buy
right.
the transmitter and receiver and put it away and
Yes.
be able to put it into the domino and transmit and receive correctly.
Right. Yeah. These are the sorts of decisions that really kind of like, they echo forward. So the right decision now will make it easier to build, to manufacture a radio. So with our goal being to enable, manufacturing, then these are the sorts of decisions that we need to pay some attention to. We need to figure out like what's the best technical answer, and then what is the best possible, set of parts. The supply chain has to be able to support it, moving forward. So that's what we're interested in getting right, or at least as right as possible. So thank you, Oscar, and I will absolutely bug you over the next week about this. Yeah. All right. Anything else from Opulent Voice? Matthew, I think you have the floor if you'd like it.
Oh, thanks. No, I don't really have any updates this week. My day job has been keeping me exceedingly busy, so I'm sorry I haven't been able to get to the lock detectors yet, but it's something I'm hoping the time will free up soon. So we'll see.
Okay. And I think just to remind me, the paper that you were thinking about modeling the symbol lock on, you were less enthusiastic about it. Like you're thinking to drop back to a more like
Yeah, I was
straightforward.
thinking, I think some concepts from that paper are still relevant, but the main difficulty with that paper is there's a hardware divide that's required. So
Yeah.
I think there's some easier approaches that get us what we want.
Okay. Yeah. That totally. Yeah, I agree. I was curious because I was like learning about cool techniques, but what you said makes a lot of sense because we had a very similar thing happen over with the AMSAT UK work for the MDT or mode dynamic transponder. There's a really super duper clever way to do it, but it turns out maybe uh, just the ordinary math will work better. And it turned out to be exactly that. The clever way requires a pretty expensive sort of implementation, and for the ICE 40 FPGA, that's really not something that can be crammed in there. Yeah, it comes at the expense of the entire design. So yeah, this is the sort of stuff we deal with all the time. That's the trade-offs.
Exactly.
Hey, Matthew, anything else? Or
Well, no, not this week. Thanks.
okay, cool. Well, thank you so much. Yeah, more soon. We'll just keep plowing ahead.
I remembered
Oh, good. What you got?
one of the things that makes a lab call, a bench test between two different radios important is that they don't have exactly the same frequency reference. They may be off in frequency, they may be drifting differently, and so on. And so being able to do some tests with different frequency references is important. We started out with Pluto revs A and B, which did not have a way to use an external frequency reference. And they have kind of poor internal references. And we graduated to a Pluto Rev C, which does have those connectors, although you have to bring them out from inside the plastic case. And we had good luck with external references, taking out that uncertainty. And then we could, by separating two radios to two different external sources, we could actually add frequency error. The Libre SDR that we now have to use because it has the 7020 and has room for our design in it, has a connector on the outside for an external frequency reference. Yay. I bought some interface cables with the right little weird connector on it to click onto those ports with hopes of doing exactly the same thing that I was doing with the Pluto. But this is where the weirdness of the design and the lack of documentation in Libre SDR is biting us again. There doesn't seem to be any way to actually use that connector. I'm told by everybody who has experience with this device that it doesn't cope well, at least not in his design, with uh, with the use of external reference. That's going to have to be investigated further because I really need to be able to control the frequency reference. If I can't do that, then I'll have to rely on internal oscillator, which is supposed to be better. It's supposed to be a VCTX DCXO in the Libre SDR. I don't have any evidence about whether that's true or false yet. And then I can dial in software offsets to the frequency to at least simulate a frequency error, but it won't be as nice as having an external reference and doesn't give you any way to really lock the two together. So this is going to get in our way, and I don't know exactly what the path to a solution is, but that's a thing that we'll have to keep our eye on and work on over the next few weeks.
Wow. Okay. I'm going to err on the side of optimism and say that surely the people that put this board together had some thoughts about external references and that we're just missing something. And if not, then the software corrections will have to do for us. And this is just a lesson for when we design our own board that we get the get the clock reference right. So
Yeah,
wow. Okay.
it's very easy to build hardware into a device with the idea of getting it fully supported in software or firmware or bitware uh, at some time in the future, and then not to get there for all of the things you added. And since we don't even know who these people are and don't have connection with anybody who was involved in the design of the transition of the design from the Pluto reference design to the Libre SDR, then um, we probably won't get any help from them.
Well, a lot of other stuff has been done right. So I'll be a little bit optimistic and think that we just need to keep plowing ahead and doing the same thing that we've been doing and reverse engineering the design and seeing that things actually do work. So hopefully hopefully we won't have to settle for some sort of, software adjustment that may get close, but not quite. Yeah, we'll see. That's a really important thing to know. And yeah, thank you for figuring it out. Is there anything that you need in order to make this move forward? Like, is there anything you don't have or any? I mean,
Well,
it's the road
among things that are
all of
available
us,
in the
but
world, I'm not sure that there's anything.
okay.
It, it'd be nice to have something like the Libre SDR that was fully documented, but the Pluto never even reached that with
Right.
the backing of a giant corporation. So
Well,
we'll have to settle
again,
for what we can figure out and move forward.
it's a lesson for us to just make sure that we try very, very hard to do a better job um, when, with all the things that we do. So,
Yeah. We will try our best. We necessarily rely on underlying layer of hardware from other manufacturers who may not have reached that standard. So there
sure.
may be stuff in there we can't document.
All right. Well, we'll
Have to
just keep
say,
doing our best.
have some documentation to saying, at least to say that there's no documentation available.
Hey, sometimes that's the best thing that you can possibly get. Better than nothing. Yeah, thank you. And yeah, we'll keep hitting away at it. Let me know if there's anything that we might need to figure it out. All right, any other Opulent Voice progress? I did complete a documentation project. So for the modules that I know a lot about, so I didn't, Matthew, I did not go in and update any documentation like the header or the body documentation for your work. Mainly because it's got there's a few comments in there where it's critical and there's an explanation and it's pretty clear, even by the title, and the code's clear and well written. But for my modules, I went through and tried very hard to kind of explain the theory of operation and try to like put that in the source code. So I finished that over the past week. And it would be great if someone took a look at it to say if it's good enough. or if it's fallen short, or any critique or comment would be welcome. So that's something I managed to do. I've been wanting to do that for a while because my documentation styles changes over time. And I looked at these different modules and, well, this was kind of scattershot style. So it's now kind of coordinated, and the stuff that we've been talking about in the meetings and that I've been, reporting here really needed to actually go into the source code so that folks have it. Originally, I was going to have a sidecar document, like each VHDL module would have a markdown. And then I did try it, and I didn't like it because it can get lost. Or, if people are just focused on the value is the source code, so the source code really needs to have the documentation in it. So after some back and forth, that got complete. So I think we're in decent shape, but take a look and see if it's good enough, if it's up to our standard, and let me know if it's not. So I just want to let everybody know that was something that got done. We've been talking about that for a while. We are planning to have a webinar later in the year. So this will be later in 2026, where we talk about FIFOs, or first in, first out structures. And this will be sort of online. This will be a virtual sort of party for donation. You can show up and hear some lectures and get all sorts of resources about FIFOs. We're going to talk about all the different options that you have from different companies like Xilinx, their FIFO IP. What is a FIFO? Why do you care? The basic theory, and then why we use a dual clock FIFO in our design. Why have this? Why do you need it? And this really is kind of a sneaky way to talk about clock domain crossing, which is a huge part of digital design when you're talking about FPGAs and ASICs. And it can trip you up, and it will cause problems. In fact, I think the bug, one of the very recent bugs that was preventing us from getting receive, turned out to be a clock domain crossing bug. And the bug that we have right now with the very first frame from Opulent Voice getting trashed, maybe not strictly speaking a clock domain crossing bug, but it's related. So this happens all the time, even to very experienced designers. And trying to put together a sort of a webinar workshop about FIFO design, both in general purpose processor languages, so FIFOs in C and C++, but also with a special emphasis on like the dual clock FIFO design that we have in our design, and also the work that Matthew's done for the clock domain crossings for the register accesses and all of the ongoing work that he's done there. So what I'm trying to do is capture all of that and kind of present it in an accessible manner that's useful for people to kind of help move this further along and get folks more up to speed with this particular technical challenge, because it's kind of a interdisciplinary one. It doesn't really get brought up in school. I never heard about this problem when I was in school, and it's one that can kind of get you. So please look for that, and I'm looking forward to incorporating, Mike Matthew's work on like peak RDL, or the register descriptive language that he kind of surfaced and brought to our attention and implemented in design, and then revved. We went from one type of RDL framework to another. That was amazing, and that is sort of directly related to this. So register accesses are very frequently a clock domain crossing, and having a framework and having a way to describe your register accesses is a huge step forward. So all of that we're hoping to capture in the event. All right. Anybody else with any sort of Opulent Voice or any FPGA work updates? Anything I forgot, Paul? Okay. All right. So FOSDEM.
I did.
Oh.
Sorry, Michelle. I did have a question for Paul. Last week when you were running the lab demo, was that just free running clocks, or what clocks were you using?
Those were the free running clocks of the two newer Libre SDRs.
Oh, okay. All right. I was just curious. Thank you.
Yeah, I think you want to track down something with the USB headset. and the clock relationship there. You want to talk a little bit about that?
Yeah, this is just a hypothesis at the moment. Um, this microphone is a Rode NT1, fifth generation, which means that it's got both an XLR connector, which is a fully analog balanced pair thing, and a USB-C connector. And the USB-C connector is basically a sound card built into the microphone so that it does its own sampling. And the claim to fame of this particular microphone is that it can put out samples in floating point, 32-bit floating point, which has a huge dynamic range and means you might not need to worry too much about microphone gain at recording time, which is a big deal for recording people and hi-fi audio and is just in the way for us. It can also do fixed point, which is what we're using it in. But my suspicion is that it may not have um, a highly accurate clock. And Interlocutor relies on the clock of the sound card to time everything. And if that clock is off by a few ppm or maybe more than that, it could have unfortunate consequences. I was going to say unforeseen, but they're fully foreseen, unfortunately. Um, I think maybe some of the problems I was having last week, and nobody complained, but I thought the audio quality was not as good as it should have been. Um, and I don't know why exactly, but it could have been some clock drift problems. And that sort of thing also cropped up in trying to debug with the Tezuka version. It looked like it was syncing up with the frame sync word just fine, and it was staying in sync for a while, but couldn't even make it all the way through the frame. Maybe 39 bits or so was a kind of a typical number, and it would drift off and uh, start to make mistakes, and then by the end of the frame, it was just gibberish. That looks a lot like a clock sync problem and clock drift, extreme clock drift. Um, so I wanted to blame that microphone. Uh, maybe, maybe, I don't know yet. The headset I was using before that, which is this, is a cheap piece of stuff from Logitech, and it seems to have clocks that are fine, but the microphone is tiny and cheap, and the headphones are not much better, so it's not going to be a source of high fidelity audio either for other reasons. Um, this microphone that I use is an analog mic plugged into the world's cheapest sound card, which is a USB thing plugged into my Mac here, and it works fine.
Yeah, I think the sort of the if you it's kind of not really accurate to call it a secret, but the secret of Interlocutor is that it uses the audio card for their hardware interrupt to run the 40 millisecond timing for the frame. So if that's wonky, um, then the whole thing will be wonky because that's how Interlocutor works. And Interlocutor is the part of our system that produces the baseband data frames. So it frames up your data. It handles the human to radio interface. So it collects your voice and your keyboard chat and your data file and whatever else. Looks at your configuration file, figures out how you want to use the radio resource. So a lot of stuff is happening there. The modem handles like the randomization, the forward error correction, and the interleaving, and the modulation, the actual like turning the bits zeros and ones into the minimum shift keying signal. So the separation of those two things means that the 40 millisecond at frame timing tick has to come from somewhere, and we picked Interlocutor for this. So we're discovering all sorts of interesting things and writing about them as best we can and testing them out. So
Yeah, it's sort of like the clock domain situation, only on a much coarser scale.
yeah.
But Interlocutor doesn't have to get every bit time right. It doesn't even know about bit time, really. It knows about bits, but they're not um, in real time until they get all the way down into the hardware. And even Dialoga, sitting in between Interlocutor and the hardware, has a pretty coarse definition of time, like milliseconds. And if it hits within a few milliseconds, it's usually fine as long as it's on the right
Yeah.
side of the boundaries.
To be honest, you have almost a whole frame too, because you have a FIFO at the, when you enter the HDL. So we have something going on, and we'll figure it out.
Yeah. So that these problems usually only become an issue as time accumulates, right? The 40 milliseconds can be 39 or 38. It works fine as long as it's not always 38, and then it'll eventually skip a frame.
Right.
Even that you might not even notice, except as a slight degradation of voice quality.
Can I interject something?
Sure.
Yeah, yeah, like if you're using a FIFO, if the rates in and out rates aren't exactly matched, you will eventually overflow or underflow your FIFO. So quite often, like you could, there's a couple approaches here, and if I'm understanding right, that could approach. Like Ethernet has interpacket gap between frames that resolves uh, clock differences at the transmitter and receiver, so they absolutely can be asynchronous. But if you have a protocol like SDH or Sonnet, they have to be synchronous, and so you have to actually do clock recovery from the data at the receiver in order to match the clock rate. So I don't know if that's maybe what we're seeing here is like a mismatched data rate or mismatched clock somewhere along the line. If we are, then there's certainly techniques that can be used to address that.
Right on.
I hope not. I mean,
I hope it's
Well,
something
I mean, it's very
similar, but
common, right? I mean, I've spent a lot of parts of my career doing clock recoveries for fully synchronous systems and that sort of thing. So it is.
well, if we've accidentally developed a fully synchronous system, then you can go back and redesign it because it doesn't need to be fully synchronous. This is a packet system with 40 millisecond.
Right, but I mean,
Yeah.
but the other underlying audio, right? If each audio card has its own clock source, 48 kilohertz on one clock on one audio card is not 48 kilohertz on another audio card, right? So you might have a few extra samples, taken along the way that get lost, or you have not enough samples just because those clock rates aren't exactly matched.
Yeah.
yeah.
As long as that difference is small, though, and as long as you're talking about audio, no problem, right? And lose a sample here or there that human will never know.
Yeah, yeah.
Yeah, we're hoping that's the case. So we'll just keep digging and make sure that it's not some sort of problem that we need to expand out to other parts of the design. So, and I don't know, I think maybe you're being a little too picky about the audio quality. I know that that's our highest priority, is to make sure that we deliver excellent audio quality through the system. It really, the variation in microphones and speakers is huge, and cheap headsets are cheap, and that's not a problem we can solve. So as long as we're delivering accurate, beautiful, quality audio, if there is a problem with the actual equipment, we don't want to be too quick to blame that, and we want to blame ourselves first and fix everything that we possibly can. But if we can objectively kind of prove out, make sure that there's nothing weird happening, that there's situations, if there's a common set of situations that we can flag and fix in our software, then we should. And if this is one of them, then let's keep at it. But there's a limit to what we can fix. So, really cheap condenser microphones, we might actually have a system that can expose that weakness, and other digital audio projects in amateur radio definitely don't. Their audio is just simply not good enough to really kind of press that particular part. So I not trying to be argumentative, but there's only so much that we can fix, and we should fix everything that's under our control, and then maybe make a very compact, clear, like, your audio equipment will affect the, our system's good enough. We can spin it in a particular way. The system is really good enough to where your equipment actually does matter. That if you have a super cheap microphone, people are going to hear it. And that may be where we end up. I don't know. It'd be a nice problem to have. So let's try to
I think
figure out if there's anything weird going on with interlocutor that is doing something that we do not expect, and to make sure that there isn't anything weird about the 48 kilohertz transition, which I don't think there is. We've done this in a very standard way, but let's do the best due diligence that we can to make sure that we're delivering the quality that we are assuming we're delivering.
Yeah, we know from early experiments that the vocoder is good enough to reveal the difference between a good microphone and a great microphone, um, which has never been true before in amateur radio, except for the people who are doing pure analog on AM
Yeah.
and a few people who are using very expensive SDRs like Flex radios that have a lot of tunability. Some of them have spent the time to calibrate their microphone and get the right adjustments in, and it does sound better. But then again, that's an analog system. If we can simulate that and do even better with a digital system, then that will make me happy.
Cool. Okay. No, it's good to air this out and to discuss it, get it kind of on the record. All right. Anything else? All right. Awesome. No, looking forward to next week for sure. We have a presentation coming up from Ever East at FOSDEM, and those preparations have been made. He's in good shape to give the talk. It'll focus on sort of the Opulent Voice, but also introduce Open Research Institute and to discuss our mission and what we're after, and to invite people to participate. So I'm really looking forward to this, and huge thanks especially to Ever East, but also to the FOSDEM organizers who agreed to our proposal. Since this is an in-person event only, that was a really nice thing for them to go ahead and say yes, even though we did not have a speaker identified when we applied. And I'm very much looking forward to watching the recordings of the talks and to see all of the different things that come out of this year's event. So this is focused on free and open source development and both software, hardware. There's been a lot of amazing things that have been presented in the past, and it's a real honor to be included this year. So thank you again to Ever East for agreeing to present. And that's coming up on the 31st of, so just 11 days from now, in very, very late January, early February. Next project. This is sort of some exciting work. So as some of you have already met Martin Lang and the other folks from AMSAT-UK that have presented here. And so AMSAT-UK is the amateur satellite or amateur radio service satellite folks from the United Kingdom. And they have a launch coming up called the FunCube Plus. The FunCube satellite is a highly successful, very interesting mission, and this triggered the development and distribution and sale of what's called the FunCube dongle. And this is something, if you are familiar with the RTL SDR, this is a very, very similar device. So USB plug-in, get a cool SDR. And they are looking at doing a digital experiment called the mode dynamic transponder. And when it was first proposed, first learned about this at the AMSAT-DL symposium this past October. There was a presentation about the FunCube Plus. It sort of sounded like they wanted to take uplinks and then fast uplink and then meter out the downlink slowly, because on a LEO satellite you have a limited power budget and you can take in all sorts of communications that may be bursty. One particular pass may have nobody, another pass may have 5 or 6 people. And so what you do is it sounded to me like they were after more of a store and forward, where you take fast uplink, digitized data, and then you then meter it out over maybe multiple passes. So not exactly. What Martin was more after was more of a signals intelligence type of thing. It was like, okay, so we have 30 kilohertz that we're looking at down from the satellite, and we want to really focus on weak signal work. We want to be able to capture and to kind of like transport weak signals. And I was like, oh, so that's kind of a different mission. That's cool. And I told him before the holiday I would kind of dig into this and start asking folks that know how to do this sort of work and get their advice. So I have some progress on a Python model that'll go into the existing mode dynamic transponder repo. So the original question of like just supporting just amateur communications, so like known digital signals, and you have a fast uplink and a slow downlink. We did some modeling for that, and that that was presented a while back. So that's a Python notebook that's going to be in the repo, and the one that I'm going to show you today, which still stumbling through and getting it to work, will go in there as a sort of a separate project, because when you talk about supporting communications, known communications, that's a different thing than just listening and digging out weak signals, and then I guess sort of transponding them back, over time in a slow way. So that part I'm going to have to ask Martin about, to like, exactly, is this the same model as before, or do you just want to say statistics about it, or what? Like, are we enabling communications? Are we prioritizing the weak signals? What are we after? So the I'm assuming the basic architecture is the same. It's a particular STM device. It's a STM general purpose processor, but he picked a pretty powerful one. But he picked the ICE40 FPGA, which is a relatively small FPGA. Why? Because of power consumption. So he wanted us to limit all of this to half a watt. Well, the SDRs that we've been dealing with, which we consider to be kind of small, like the Pluto and the Libre SDR, pull like 2 watts plus. You could get it down to 2, maybe below, if you do some tricks with like the, limiting to one transceiver instead of 2, and turning things off, turning off parts of the chip. That's basically how you save power when you're in an ASIC. So you can get it down, but half a watt, no, not going to happen. So the stuff that we've been using in the lab kind of routinely is not what you would put on a LEO satellite with a half watt power budget. But the ICE40 does come in under that. So our method of offloading as much as possible to the ASIC, to the FPGA, and then reserving the general purpose processor for the cool stuff, the cool things, well, that won't work for the AMSAT-UK proposal. More stuff has to be done in the STM, microcontroller, and you have to like say, okay, what is the FPGA really, really good at? And I think that we have a solution for this very ambitious sort of proposal from Martin Ling. So I'm going to show you the top part of the Python notebook, so that you can kind of see it firsthand. Let's see. All right, let me get it working. There we go. Okay. Everything will be fixed in post. That's what I tell people. Okay, here we go. This is called the SIC receiver. And SIC is a technique in digital communications. It stands for successive interference cancellation. So the successive is kind of the giveaway. What you do is you have a bandwidth. You're looking at, like, in this case, 30 kilohertz. And you are going to go over this bandwidth, and you're going to say, what are all the signals that I see? Like, maybe there's none, 1, 2, 10, whatever. So you're going to like scan, and you're going to go, oh, wow, look, there's 2 powerful signals and there's 1 smaller signal. So successive interference cancellation is the first time you go through, you take the heaviest hitter, the biggest signal, and you go ahead and you say, okay, I now know what samples from my, IQ farm, which parts are related to that big signal. Now you might go ahead and you might demodulate, decode, whatever, you can handle that signal. But you when you go through, you identify the signal, see the energy, and then you take it out. Now you go back through again, and you go, okay, to the next biggest signal. You deal with that signal, process that signal, whatever you want to do with that signal. Then you take it out. So you're canceling in succession things that are interference.
Excuse me, Michelle.
Oh, sure.
Are you showing the right slide?
You should see SIC receiver.
Okay.
Reference. Yeah. You should see like it looks like a web page, because it is. This is my Jupyter notebook for successive interference receiver reference. Yes, that you should see that. Is that what you're seeing?
Yes.
And it's moving. Okay, yeah. I'm just showing you, this is the Python notebook for the model. So if we're going to design it, then we need to be able to model it first, and so that's what this is. So yes, you should be seeing that. And then now you've worked your way down to the weaker signals. So you've taken out more powerful signals, and now you're working on the smaller ones. And so when you delete a signal, you kind of lose those samples. You zero them out, or maybe you put them at the noise floor or whatever, it depends. So yeah, you can think of it as like you have a slice of cheese, and then you have a hole, and then you have another hole, and you have another hole, and then it looks like a slice of Swiss cheese. That's sort of what you're dealing with, but you still have a lot of cheese, right? At the end of the day, you still have all of this stuff, and you have a lot of weak signals you can work with. And so this is what you do in cellular, and it's what you do in signals intelligence, and it's what you're doing, in a lot of interesting cases where you have multiple signals on a band. So can you fit this into a ICE-40 for an amateur mission? And I think the answer is yes, you can. There's going to be a limit. There's an upper limit on how many different interferers you can work through before you get to the weak signals. And that's based on how much time you have between going through and getting a sample of your 30 kilohertz. And that's where the FPGA comes in critical. And then the other question is, can you actually ship the IQ to the general purpose processor, to the STM, fast enough for it to do all of the other work, all that radio work? Like, oh, here you go, here's an IQ. Can you figure out like if this is SSB or CW or whatever? And the answer turned out to be yes. The communications that Martin has set up between the ICE-40 and the STM are an SPI bus, and it's fast enough. Even if the worst possible case, it's actually fast enough. So that was the first thing that I kind of checked off, and I probably need to do a better job of documenting it here, but it's going to be okay. All right. So I just summarized all the purpose, but it just kind of told you about. This first kind of grayish rectangle here is importing all the libraries that we need. For Python, it really shines when it has all these different libraries. And if they don't load for you, then it flags it and it says, if you don't see libraries loaded successful, it doesn't. We are using something in Python called data classes to keep all of our parameters in one place. This is like a class where there's no functions, it's just variables. So it's just like a catalog of all of the different things. And the first biggest thing that you need to figure out is what kind of channel map you're going to have. And we have choices here. And these choices change whether or not we're doing this for the MDT project or we're doing it for HiFiRIA. So in order to use this for a signals intelligence or a scanning application, you need to approach this more like a spectrum analyzer. Your channels need to overlap a little bit, and you need to have a solid, even, like, doesn't matter where you are, it's all even. For something like HiFiRIA, where people are supposed to be within an uplink channel, then those channels are kind of separated with a guard band. With this model and with the eventual VHDL, you can decide between those by setting up some configurations. Then it just sets up the channel configuration. All of this is working as expected. All of the stuff that Martin told us in previous talks and meetings is here to the best of my ability. And I picked 16 bits for the data width just to start out with. The prototype filter, when you have a channelizer, when we talk about a polyphase channelizer, that's the receiver on the satellite. That's what we're going to use for HiFiRIA. That's what we're using here for MDT. When you say prototype filter, the prototype is a single channel filter. That's a low pass filter that is the width of a single channel. So we're channelizing this 30 kilohertz that Martin wants to look at. I picked 4 because it seems like it works okay. And the prototype filter is the width of one of those channels. So you're like, okay, got it. Prototype filter means, the filter that we're using to channelize, to split up our, bandwidth. And we design it here. So we tell it like, okay, this is basically build a low pass filter that has this roll off, this 3D point, this bandwidth, this pass band, this stop band, and there's lots of decisions that go into this, but it's basically like, do you want a Ferrari or do you want a minivan? You get to pick. And after we do that, we plot the filter response. This is sort of the filter response on the left here. And this is what the actual impulse response looks like. And this is related to all of the little coefficients. And that's what it's supposed to look like. That looks really cool. I'm so happy to see that. and we can compare the different styles, so are we going to overlap our channels? We're going to have more of a spectrum analyzer, or we're going to have a channelized system? You get to choose. Okay, so all of that's kind of built in and reported. When we do something called polyphase decomposition, that's a scary sounding word, and I get irritated every time I see it. No offense to the people that know what that means already, but when I see polyphase decomposition, I always think of polyphase duplication, because this is the part of the system where you take that single channel and you duplicate it out. You're going to make a structure that can handle the number of channels that you want. So we have 4. So now we need 4 filters, but we need each of those filters at the right frequency. So you take your one filter and you're going to do an FFT to shift it up to where it should be. And this is all that this is doing. It's just making a matrix. Each row of that matrix is another set of the exact same filter coefficients. And then you're going to FFT each of those rows using matrix math, which the FPGAs are so good at. So this is what we're doing in the FPGA. This is kind of focused on the FPGA work. So I talk a lot about that here, lots of comments, and yeah, I got a big fat bug here. And what I'm trying to do is kind of show the filter taps and all that. And then I go into the channelizer. So that's as far as I've gotten, but this will make the VHDL a whole lot easier to write. And the sort of proof of concept for Martin and David and all the folks at AMSAT-UK maybe a little more reassured that it's actually can fit and do what they want. And it also is extendable to the code that we have to have in the, for Hyperia. So we're going to have some sort of code that runs our channelizer for our uplink. Otherwise, it won't work. So this is sort of dual use for that. All right. So I'm going to stop the share and answer any questions. Anybody have any questions on that? If there was anything that wasn't really clear, anything I could do better, or anything that you think I might be missing? Okay, floor is open to anybody to share anything, or if they need anything, or have any comments or questions, or.
I had Michelle, this is Adrian. I had a real naive question. What sets the actual so that 30 kilohertz band is almost like an IF, right?
Oh, that's just the so no, I don't think that's the RF bandwidth. Is that there's 30 kilohertz that Martin wants to monitor from the AMSAT UK FunCube Plus satellite. He wants to monitor 30 kilohertz, and he wants to dig all the signals out that he possibly can, and then it gets a little. I'm maybe a little unclear about what you do after that. I think he wants to transpond them back down, for the satellite thing. But the part that he really needs help with is the receiving part. So that's what this is kind of focused on. So that 30 kilohertz is not IF. It would be the like the regulatory style, like the RF bandwidth that we're looking at. We're looking at the 30 kilohertz, and this would be UHF, so 70 centimeter satellite band.
Okay, that's clear. Yeah, I was wondering just exactly what the upfront actual frequency that they were receiving at, and so that's just a 30 kilohertz band slice out of the initial 70 centimeter band that they're monitoring.
Yes.
Okay, and that can be shifted anywhere along that whole hem band.
Yeah, if you wanted to deploy this, like you wanted to build a radio, so this is like we have 70 centimeters in mind for MDT, but this sort of technique can be used at any frequency. It just kind of depends on where you place those filters. All filters don't work really well everywhere. The higher the frequency you go, little teeny tiny filters just don't really work very well unless you have lots and lots of money. But yeah, this is for this particular sort of deployment, and even extending it to ours, then these filters will be very similar. They'll look pretty much the same. So yeah, what you do is you set up your filter, you develop a filter for one channel, and then you say, okay, I need 90 channels. Now I have a large matrix, and each row is the same filter over and over again. And then, there's lots of other interesting things that happen with polyphase, but that's the basic idea when we talk about filter decomposition. That's what you're doing is you're setting yourself up to have a bunch of channels, and each channel is the same channel filter. And that's the part that we're trying to nail and get down and then get sign off on so that we can go ahead and set up a receiver, a really good receiver for them. And then start doing some simulations. Later on in the Python, I got a little bit ambitious and like creating some signals to kind of like, here's some random set of signals. How well does it identify the 3 or 4 strongest signals? The one thing I'm kind of worried about is with the FPGA is really pretty small, but still, I think it's got 5,000 logic units or loops, and that can do some pretty good work there. So I'm optimistic enough to say this can actually do SIC for some number of signals. I'm still unclear as to exactly how many. I'm guessing maybe 3 or 4. And if there's more than 3 or 4 powerful signals in this 30 kilohertz, well, then you're never going to get down. You just don't have enough time to get down to the more weak ones. So that's the one thing I'm kind of worried about that I'd like, to explore as quickly as possible to kind of give an answer back to Martin. If it turns out that that's too pessimistic of a evaluation, then, and if it can do 10 or 15, then I think they'll be super duper happy. And if it turns out to be 2, then but still 2 is good, to be able to prove this and put it in space for amateur radios is a big deal. And it is scalable. That's the idea here, is to make it as modular and scalable as possible. Well, maybe not as possible, but in the direction that we need it to go.
Are you considering frequency shift or Doppler? Because the channels that you are thinking about is kind of fixed.
Yeah, that's a good point. Because Doppler is kind of a big deal, and I don't have any Doppler modeling in here yet.
It should be added, and it should be considered for cutting some channels, and just because of the frequency shift. And also the radios are not all of them properly calibrated. Some amateurs already are using time-based for GPS and things like that, but not everybody.
Yeah, no, that's a really good point. My experience with this technique is terrestrial, and you generally do not have the challenging Doppler that you do.
Right.
Well, you have the uncalibrated radios.
Yeah, and uncalibrated radios, absolutely. So yes, it was one of the reasons why I wanted to pick the overlapping style, the more like a spectrum analyzer than a channelized thing, because like, oh yeah, it might, there might be the assumption that everybody is on channel and on a particular.
No, that is ideal. Actually,
it's ideal, they're true, but
actually, you, in the software, you can add some AI for identifying the channel where it's located by looking for k-mean clustering, identification of the signals. And that is software, more software than hardware. And there are people working on identify this kind of algorithm.
Yeah.
And look forward for anomalies to correct the frequency.
True. I think for this particular application, we have an advantage over any sort of AI, and that is that we can do a brute force search over the entire 30 kilohertz faster than, fast enough to where we don't need to have any additional algorithms. So that's an advantage that you get with the FPGA. If we were only in software with a general purpose processor, then I think some additional intelligence might actually be better. And you are right. There's an awful lot of work being done here in digital signal processing with signals identification and prediction. We're our kind of secret weapon is that the hardware component, the FPGA component, just simply knows where the signals are. Now, tracking Doppler is another whole challenge. So the tracking part, like if you found the signal and you started to demodulate and then it zooped away from you. So yes, I think the whole frame of reference is going to have to be, it's going to have to be able to move. Like, and that's kind of the up to the FFT, I think. So and tracking. Maybe Paul knows a little more about this. I think he has some experience here. But for right now, for the next week, because that's maybe my planning horizon is about a week. And for the next week, I'm going to make this model work for static, math. Like, can we pull this off? And can I explain it to like all of you in a way that is accessible and easy enough to understand? Like, do you get it? Does it make sense? And it should. All of this stuff should make sense to all of us here. We should all be able to follow this. And I should be able to explain it at that level. Or I have no business writing it down and turning it into code. And so by next week, I expect to be able to show you, like, okay, here's about how fast it will be. Here's the sort of things that we need to worry about. This is the system level, this is the role of the FPGA. This is the stuff that the general purpose processor is going to have to do, the STM, which I got to tell you is a very capable part. And this is the opposite situation that we have for the Libre SDR and the Pluto, and that the FPGA is actually pretty big, and that the processor feels like it's a little, I don't know. So it's my gut instinct. So in this case, we have a very, very capable STM part, to handle like general purpose stuff, and that we got to be careful about the things that we tell the FPGA to do. But the brute force kind of like go through with successive interference cancellation. Yeah, that's just going to give us the answer. And the tracking and the frame of reference stuff, that's going to have to probably be managed above that. So we're just going to order the FPGA to shift around, and how hard that's going to be and whether that overwhelms our particular architecture, we'll have to see in a week. So yeah, but thank you. The Doppler I need to start thinking about that now, really. The first is to make sure the math works, it's stable, and then to be able to shift all of this up and down. So I look forward to coming back and being able to answer your question, Oscar. I'm looking forward to that. Awesome. Okay, we're a little over time. I apologize for doing that. So if anybody needs to take off, please do. And I just want to tell everybody to thank you so much for working so hard on everything. There's a lot going on, and I'm really looking forward to FOSDEM, and very much looking forward to whatever the future Geo folks come up with for the next meeting. They're talking about March. So try to get there if I possibly can, or at least attend remotely, and I'll let everybody know about how that turns out. Later on in 2026, we usually have a big presentation and exhibit at DEF CON, and RF Village invited us back. We've been invited to come to an RF Village in April here in San Diego for one of the B-sides. There is a big amateur radio event in Japan, Tokyo Ham Fair, I think next autumn. And we've been asked several times if we would please come to that. So there's lots of opportunities to meet and to present our work and to do demos. So if any of this sounds interesting to anybody, let me know, and we'll make it happen as best we can. Okay, so we'll close it here. And thank you very much, everybody. I'll turn off the recording. And if anybody wants to continue to talk and catch up, then I'll be here to answer any questions or talk about anything you like.
I'm driving down the road in my souped-up Cadillac, and there ain't another car inside. I passed the graveyard, the headlights flash. It looks like I'm racing tonight. Oh, but the zombie's got a 57 Chevy, and he's already caught up to me. And I'm trying to shake him off my tail, but his car's the fastest I've seen. 'Cause it's a zombie car chase. It's a of a ride. Oh, cause the zombie's got a 57 Chevy and he's never lost a race just yet. And I'm racing for my life tonight. I hope I live to forget it, cause it's a zombie car chase.